All right, greetings. I thought I thought I'd just finish this problem that we started today. Okay, so I'm going to take this point here and I'm going to measure from this point right here. So this will be cattywampus, and I'll do my work over on this side. I'll get my bar out here. All right, so this is, I mean, it's at 7.5 meters on the side. So let's just take this. Let's go out here. Even with a pen, if you're stuck on the trig, sometimes just break out a ruler. All right, I know I'm being kind of fancy here using this thing, so I want to get 90 degrees up to here, and I'm going to get it 90 degrees up to here so that it's fairly level. There we go. Now I can just use my pen or my ruler. Dun, dun, dun. Got these weapons of math construction here. So I can draw a nice little box. Sometimes just draw the freaking picture, okay? And it works out nicely. All right? And it actually did, because I tested this out on an earlier recording. So let's just go ahead and draw this. Really light thing like that. And let's draw this across here. And there's the center of my circle right here. Okay? Now, if I've got a point down here, C and B are positive, right? Because they're going this way. Their electric field is, so let's just look at point C right here. So it's got the electric field going that way. All right, and then, of course, it's going to go into this point here. And electric field lines can't cross each other. And so we also have the electric field going into this one from here. And these are vectors, so it's going to get extra. It threw me off that they had a Q there, all right? And we found out today in lecture that the same thing is going to happen here. And so let's just go ahead and look at the electric field coming out of here. It would go like this, because that might be easier for you to visualize. Here's because I can just take this, since it is a vector coming into here, I can just take it like this and go like this. All right? And so I wound up with that. And then this one, the electric field's coming in here. And so I can just take the electric field and draw it like this. Since it's going in, remember what you can do with vectors. That's the beauty of vectors. You can take their endpoints and just move them. And like that. And we found, and then this one is like this. And then this electric field is like this. Okay, and so we found, oh, well, this will cancel from this because they've all got the same charge. This will, and they're the same distance. And these two will cancel. So all I have is these four charges going up here. So all I got to do is calculate the electric field at this point using one of the charges, and I'm done. And then take its x component and multiply by 4. So how far is the midpoint in centimeters? Well, the midpoint's, it's 5.3. The distance to the midpoint is equal to 5.3 centimeters. Now, if you don't have anything to measure it with, well, you've got a distance d here and you've got a distance d here. Let's find the hypotenuse here and cut it in half. So the hypotenuse, the distance of the hypotenuse would be the square root of d squared plus d squared, which would give me the square root of 2 times d. So d to the midpoint, which is equal to 7.5 times the square root of 2, which is equal to 10.6, is 1/2 d of the hypotenuse, the distance of the hypotenuse. So that comes out to be 5.3 centimeters. We measured it with a ruler. We did a little trig with it. Well, we did a little high school Pythagorean theorem with it. Or we know that this is 45-degree angle. We know that this is 45 degrees, a 45-degree angle, and I know that D is equal to D of the hypotenuse, this whole thing here, times the cosine of 45, or I could have used D hypotenuse sine of 45 because of that distance. So let's see what happens here. So I've got 10.6 What? That's not going to work real quick. Well, yeah, that gives me what D is, and that's going to give me 7.5. 7.5, then I can cut that in half. Yeah, D cosine of 7.5. D cosine of 45 will give me, yeah, this is equal to, so D is equal to 7.5, but how does that help me find this? Oh, this distance D here, yeah, D at the midpoint then is equal to um, 1/2 D at the hypotenuse of the cosine of 45. All right, so whatever. Okay, so anyway, oh yeah, then 1/2 D of the hypotenuse. Damn it, I did this last time on the last one. I got all screwed up on, don't worry about it. It's 5.3, okay? And then here's the deal. Here's what we found out. Here's what we know. The electric field at this, the electric field generated by this charge here, acting at this point here, that E field is equal to K times QC over 5.3 times 10 to the negative 2 squared times that distance squared. That's the overall electric field, and that's a vector. Okay? But we just want, so there's the electric field coming out of QC. All right? There's that. Okay? That's the E that we just computed here. All right? But all we want is the electric field for C is equal to K QC over 5.3 times 10 to the negative 2 squared. Now, all of them are going to be the same. And so, but all we want is the y component. ECY then is equal to EC times the sine, or cosine, times the tangent of 45. What are you doing? No, times the sine, 45. Okay. ECY is times the sine of 45, so that each one of them, so all of them are equal to 4 times ECY. All of them put together, that's what they're going to equal. Not a hard problem, really. Not too hard once you get into it. I'm sorry, I kind of messed around with that a little bit. Okay? So we're done with that one.